Thanks for everyone for joining today. Today's webinar is Milling Digital Partials the Profitable Way. Our presenters today are Greg Everett from Sierra Dental Tools and Chris Schirmerhorn from Meyerson. Thank you both for being here with us today. If you have any questions, feel free to type them into the question box and they will be addressed at the end of the webinar. But now I'm going to turn it over to Chris.
Great. Thank you very much. So yeah, what we're going to talk about today is digital design, going from digital design into nesting and milling these materials with Greg. We're going to do some live nesting with Greg, and then finally we'll finish up with kind of showing you how to repair some of these materials and dealing with that. So we'll kind of take you through a total workflow and being able to produce a framework just like you would a metal frame, but guess what? No more metal. All right, so the material we're going to talk about is the Zerlex acetal. The Zerlex acetal is a highly crystalline thermoplastic. This is the reason it can be 100% dense, but also be flexible, right? So here's some examples of how it's used in other industries because of all the properties that are such an advantage with this material. You got gears and engines, nuts and bolts. This is the recoil spring from a Glock semi-automatic handgun. There's a bushing in there made out of acetyl resin specifically because of its wear resistance and impact and fatigue resistance. This piece here is in an engine, right? We talk about it not absorbing moisture. You can see a drop of oil right on there. I'm a wrencher. I got a 1966 Pontiac GTO. I also have a 1950 Mercury. And I like to get my hands dirty with those engines, and I'm cleaning my cuticles for the next 3 days. This piece of plastic here sat in oil for 50,000 miles. And you can see this is made out of an acetyl resin. You can see it hadn't absorbed any moisture. You can also see this chain. This is a tensioner. This is spring loaded, and it pushes on that chain to keep it from having any slack. You can see that it barely has a notch worn in it. And now it's in oil, right? So that's a lubricant, which helps, but it's a very wear resistant material as well. And that's a Harley Davidson Screaming Eagle is that engine, right? So relying on it, in a high-end engine and a really hot running engine, it's air-cooled engine, just all those different things. I like to give examples of how it's used and how other industries rely on it, because I've sat in webinars just like you guys have and been promised the world on stuff that didn't quite turn out to be. And so I like to use examples to, I guess, get my point across. So that's a little overview of what we're talking about here. Zerlex acetal is not another PMMA. This is not another, simple plastic. This is a pretty advanced, really strong plastic, 8 to 10 times stronger than the strongest PMMAs. And that's why we're able to make something like a framework where it can compete with metal. It's not going to be everything metal can be, right? They both are going to have their pros and cons. But as far as it being a replacement for metal, in most situations, I believe it is. All right, so let's talk about design. All right, so in 3Shape, as well as just about every other partial design software, you're going to position it for your path of insertion. Once you position it for the path of insertion, it's going to show you where your undercuts are. It's going to show you the red being the most extreme undercut, the orange being a lesser undercut, finally with the yellow being a slight undercut. With the tip of a clasp, you could definitely get into the red. The middle of the clasp, it's iffy if you want to get into red. I try to stay into the orange or yellow. And then at the base of the clasp, or where the clasp attaches to your partial, you definitely want to be above the height of contour. You want to follow the same rules as metal when it comes to that part. Of course, the extreme undercut going into the red and orange with the middle to tip of the clasp, that you wouldn't do with metal, wouldn't flex, wouldn't go into that undercut. But when it comes to where it rolls around and is going to attach to the major connector, that's where you do want to follow those rules and stay at or above the height of contour. All right, so again, the clasp is going to come across here above the height of contour, then it can go down into a deep undercut. So once you accept the path of insertion, the software is then going to block out, depending on your settings, but I recommend you to set it at a 0 degree, right? So it's going to block out from an undercut straight down. It's then going to block that down. You can then go in with your waxing tool, it has a plus or a minus or an equal. Plus, you can add wax, minus, you can take away, and equal to, you just kind of smooth what's there. So we're going to click on our minus, and we're going to go across here with this little circle, and you're going to expose, take away wax, and expose the undercut. We're going to stay above the height of contour here, very important, and then go down into the undercut. Don't forget about the lingual. All right, this is a material that is flexible. Metal frames don't flex, so we have to totally block out or mostly block out the lingual areas. With this material, you can actually expose some of that undercut and let the major connector flex in and actually gain retention if you have limited retention on the facial where your clasps are going to be, and let your clasps be reciprocating and let the major connector actually be retentive. So don't forget about that with this material if you have limited undercuts. Right? With 3Shape, the next choice is going to have you to block out, or I'm sorry, create an outline for where your mesh is going to be. All right, this is going to be just like a metal frame. You're going to create a mesh work. So you're just going to go around and outline. Back here in these tail pieces on a freehand extension, put a nice large oversized tissue stop. On these short little guys here, maybe not such a large one, but keep in mind, you're going to be trying this in and it's a flexible partial. And the doctor may push in the back, and if there's not a nice tissue stop, it could have flex or movement. Think that the partial's not fitting, when really, once you get acrylic on there, it actually will be stable. But we need to let the doctor know how stable it will be or whether it's fitting or not at the try-in. Also, we're going to be packing acrylic to this later on, right? Either packing or injecting or however you do it. And that's thousands of pounds of pressure of that acrylic being squished in there. If you don't have nice, substantial, large tissue stops, that framework can move and warp. And everything fits good with the frame when you invest the case. You pack or inject the acrylic. When you divest, all of a sudden it has a weird bounce or an ill fit. And that has a lot to do with not having a nice, large, substantial tissue stop. I may even put one up here in the anterior, even though we have abutment teeth. You may put one there and one there. If you have any doubt, put a tissue stop. You can always take it off after, or even if you leave it, they're hardly noticeable around the acrylic. All right, so there is a DME for the Zerlux acetal, but very simply, there's just 3 things that you change. All right, one is your major connector. Your major connector, if it's a normal width, right? So if the palatal or the width is normal, you're going to want to be about 1 millimeter to maybe 1.2 millimeters in total thickness, right? So there's a waxing and then a major connector thickness. Set the thickness at about 0.8 and set the waxing at about 0.1 or 1/10. And the waxing just blocks out all like the rugae and any sharp angles. And when you do that waxing combined with about 0.8, that'll put you at about 1 millimeter, 1 to 1.1. If you have limited width in your major connector, you want to thicken it up, right? Because if we can go wider, we can go thinner. If we can't go wider because there's limited space or the design doesn't allow for it, we do need to go thicker, but I wouldn't go any thicker than 1.4, maybe 1.5 millimeters thick total. As this material gets thicker, it can actually become weaker because it loses its flexibility, and that's where this material gains its strength, is because of its forgivingness. Metal gets its strength because it just fights against everything. It's strong stuff, there's no doubt. This material, gives. I mean, the building that I'm in right now, it has a lot of steel in it, and I'm happy it does, but I wouldn't want steel tires on my car. They're going to wear out in no time, right? And so we need to have that flex to make sure that it does allow. The second is our gap, right? So this is the block out under the mesh. We want that at 8 to 9/10. We want more block out than what's normal for metal. And then the actual mesh itself, you'll see in my design, I like large holes, right? I don't like a bunch of little teeny holes. I nice large holes in the mesh. And I like to have that mesh at about 8 to 9/10 thick. So thicker. And that's really the 3 measurements that are in the DME that are changed from just default. So you can decide if you want to import DME or if you just want to change those in your settings or create your own DME. And here's what mesh looks like, right? Nice big diatoric holes or whatever you want to call them, meshwork holes. And then the thickness of it, the block out under is 8 to 9/10. The mesh itself is 8 to 9/10. Next, it's going to ask for your major connector. And here's what I was talking about, your structure thickness, which is your major connector, 8 to 9/10 with your waxing at about 1/10. That's going to put you at about 1 to 1.1 per tenth. And so I would leave the waxing because I like to see the rugae showing through. If the higher you take this, the more it'll dull that out and make it so that it's more flat. And I like to have the rugae. That's up to you, but I like the rugae. And then with this is where you'd want to affect the total thickness. But this combo here puts you at about a millimeter, millimeter one, somewhere in that range. All right. So then you'll mark, click, click, click. You'll go around. We aren't going to have any texture. All right. The reason we have texture on metal is so the glimmer, the mirror effect, the shine gets broken up. Don't have to worry about it with this material because it's not going to do that. So just choose a smooth surface. A lot of times you can kind of mark this secondarily to the major connector, so this part becomes smooth and this part has a texture to it. You don't have to worry about that. You can skip that and just mark it all total. Make sure you overlap your mesh. One thing with 3Shape is where you mark your parameters, you can't really change. You can add to what you put there, but you can't really add your parameter to your parameter. So you always want to overlap things to make sure they really join together, and then you can smooth things down from there if needed. And so this is kind of how my major connector comes out. I don't put any bead line. Reason I don't put any bead line is, you know, we're looking at a flexible partial. And let's say we bead across here and this is really bony. Well, we're gonna get a bounce on this tail piece because it's gonna flex around the bony area, not unlike metal. You know, metal will just smash it out of the way. The patient will have a sore spot for a few days. Tissue will heal, and like we've all seen on repairs, they'll have a dent in their palate from that partial. The reason these are popular is because they're comfortable. So it's not gonna do that. It's gonna flex around, and that can cause a bounce. All right, just a different view here. You can see the mesh. If you ever get open areas, you want to close them, you could just tell it that it's a clasp or something and click, 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 add it on and fake out the software, and you can kind of close some stuff up. Clasps. You know, we thought about creating a DME for the clasp, but every clasp is going to wind up being very different from the other because it's a flexible material. All right. Cool thing about this is you click on one of these points, spline points are called, and then you can hold your control and or shift and roll your mouse button. It'll make it go wider just by rolling the mouse button, or fatter, or if you hold control shift at the same time, it'll go wider and fatter. And so here's, you know, kind of how you want to design it, right? And so generally we're going to be here 4 millimeters wide. The wider we go, the thinner we can go, right? We're going to be setting a tooth here later. Your denture, your setup guy is going to be setting a tooth, right? So you don't want this big fat little bump here that he has to try to set that tooth around. So if we go way wide, you can go much thinner, and then he can sneak that tooth up really close. And then you can kind of taper it down. So here you're going to be, you know, 4, and here you're going to be 3-ish, 2.5, and then tapering down to a point. Definitely not metal, right? So these aren't the thicknesses of metal. These are what you're, you know, this is one of the sacrifices. Metal clasps, metal major connector is going to be thinner. There's no doubt. But a lot of times patients notice these less because they're lighter and they don't have the you know, the metal taste and the hot and cold sensation. When they drink hot coffee, that metal gets hot immediately. When they drink cold iced tea, it gets cold. This acetal won't do any of that. And so you can see you can go smaller if it's a smaller class. It's all about leverage. I would recommend that you guys over design the clasps for the first few cases, and then finish them down how you would like them, right? Talk to your manager, talk to your, you know, get in your own head and decide how you want to design these. And once you decide and you shape one and you get the good flexibility you want, take your calipers and measure it and write down where your measurements are. And whenever the next time you design one, as you roll that mouse button, you know, it'll tell you the thicknesses, and then you can start to really dial it in to design those how you would like it. Some like them a little fatter so they can go less wide. That's okay. There's limitations there, but you know, there's also some advantages, and vice versa. Make them flatter and wider, and that might be the way you like it. But always go bigger because you can always take away material. It's possible, but it's more difficult to add it. All right, so we talked about overlapping. There's always going to be a little kind of a dip or a bump there. You can take your waxing tool and smooth everything and make it look nicer. And here's how kind of you'll look from here. Next, we're going to do our finish line. Finish line's the same as the clasp. You just click on a spline point, hold your shift or hold your control depending, and it'll make it wider and then taller. And you want to have a more substantial undercut here so that that acrylic really locks in. You know, this is a flexible material. We want it to be flexible where it's going to be flexible, but we also want it to be more stiff. And where we want it to be more stiff is that joint between the acrylic that we're going to place here and the partial frame itself. All right, another view of that finish line, making it nice, robust, so it really locks it in. And here's our finished design. You can see you can go along and smooth things. I like the rugae showing through. You know, I think that'll feel familiar to the patient's tongue. Different view, you can see these need to be really flat, right? So that we can really abut that tooth up against there. All right, and here's an example of a design. This one was done in 3-shape, just so you have a little example of that, but really the workflow you just saw is not exactly the same, but super similar. So if you're, what you just saw with 3-shape, it's gonna have its similarities on the ExitCAD side. So nesting, you know, Greg's really gonna to get into nesting as well as milling. This is VHF. That's what I use quite a bit. I also use Millbox. I have one mill on Millbox. I have the other one on VHF. So I'm, you know, familiar with both, and you know, all of them. It's just like the design softwares. They all have their little differences and their little advantages. Nice thing nowadays, you know, it used to be even 4 years ago, you'd come across CAM softwares that didn't even have a choice for partial frames or anything like that. And nowadays, everybody's starting to gear up and change what they do so that the removable side of our industry is actually really coming. Greg is going to talk about some really cool things that are happening to where now all of a sudden milling speeds are starting to compete and even beat some printing speeds. And so that's really, really exciting. All right, so now Greg's going to take over and kind of talk about, you know, nesting and kind of the cool things they're doing with milling. Go ahead, Greg.
Yeah, thanks, Chris. That was an excellent walkthrough, by the way. For those of you who aren't familiar with Sierra Dental Tool, our claim to fame has always been, you know, bringing that extra value, that extra efficiency to the lab. And when it comes to machining plastics, there's some nuances on the tooling side as well as the CAM side that can really help you be successful. Chris is driving, so he'll click next to the next slide there. One of those things on the tooling side is the geometry and the finish on the tool itself directly affects the output and the dimensional tolerances that you can achieve with your dental milling machine. So what we've done at Sierra is we have a proprietary technology that's called lapped edge technology, and we actually have a secondary process that the edge is post polished after it's ground. And you can see the lower image on the left is what a typical tool would look like under high magnification, and ours is post polished, so you actually have a very, very sharp knife edge edge. And what that does is it drastically improves the surface finish on the parts, and also because the tool starts off sharper, it lasts longer. And the surface finishes that we're getting with this tool is amazing. You know, it's almost ready to use right off of the machine. That's one aspect of it, and then the other aspect is kind of related to the CAM software and the tooling, and that's process time. So in order for these things to really be profitable for a lab, you need to be able to produce them, you know, fairly quickly. And so, you know, at Sierra, we work very closely with our friends in the industry, you know, Meyer Sim Systems with Millbox, and of course Zahn. And so, as kind of a collaborative effort, we've come up with a solution that really improves the the results that we can get off with this material here. So go ahead and jump into the next slide there, Chris. So at the core of the solution is actually a completely new tool. And this tool implements the same edge treatment that we're known for with our plastic tools, but it's also a completely different geometry. And this particular tool is designed to remove the waste material extremely fast. So for instance, the old way of doing it was to rough with a 2 millimeter, go to a 1 millimeter, and then a 0.6 on detail. The new system, we rough in about 25 minutes with this tool, whereas with the 2 millimeter, the roughing stage would have taken a couple of hours. So the time savings is drastic. Usually direct comparison, it's about 40%. And so now, like Chris mentioned, we're at a place with this where it's, you know, at or faster than printing times, and then you also get all the benefits of the really high-end Zerlix acetyl material. So yeah, this is what we call the rapid removal razor sharp tool, and it's currently available on the Roland system. So those of you guys who are running Roland, definitely something to look at. Now we'll jump into the next one here, Chris, and I've actually got a video of it running, just running in wax as an example of how fast this thing chews up material. And so it's taking a 3 millimeter pass in wax, and this entire experiment, we reduced the puck to nothing in 8 minutes. So it's not quite that aggressive in the acetyl, but you can just see the way that it makes material fly. So like I said, typically like an RPD frame will take about 20-25 minutes to rough, and then you're moving on to the finishing tools. So next one there, Chris. Couple of points on the razor sharp tool. You know, we're moving material very fast. I've already touched on the geometry and the importance of the cutting edge being very deep. We've also implemented some designs, some design characteristics in this tool that allow it to go extremely deep in the puck and without clogging up. So we can mill up to a 35-40 millimeter puck if you really needed to. And at the bottom there, you can see the Zahn item code there. That's, like I said, it's available on the Roland system. So now moving on, I'd like to do a quick run through on how to nest an RPD, and I'm going to run it in Millbox. So Katie, if you can switch me over here, we'll jump on. Okay, hopefully everyone can see my screen.
Yep, I can see it, Greg.
Excellent. And all right, so what we'll do is I'll show you guys how to start a new project and run it, and then we'll look at a simulation. So those of you familiar with Millbox will know this workflow. It's the same in other CAM systems. You're basically just going to bring it in. You're gonna nest it in a certain way and then calculate it. So I'll calculate it for the 51D. Select your fixture, and then here's Chris's beautiful design here. And we're going to import it. Now, one thing to know with the large tool, if you're going to implement that, the offset around the part needs to be enlarged. And you'll see that here in just a second. So because the tool is 3 millimeters in diameter, you need space for it to go around the side. So we'll just bring in a test puck. And you can see the extra space here. Now this is set at default currently for the material. If you're nesting in a different, if you're using a different setup, you know, be sure that you have adequate room for the tool there. So I actually need to turn off the default sprueing in this version, but I'll just get rid of these real quick and then we'll sprue it. Now, as Chris kind of touched on, the material, because it's flexible, that's why it's good material. However, that does present some challenges when it comes to machining, because as the tool is doing its cutting, it's putting a force on the material, and if the material has any sort of mobility in the puck, it can be deflected and you can lose dimensional accuracy. So the spruing stage is actually quite important. What we like to do is run a tapered sprue. And the reason for that, again, is because we've got that larger offset, so it's a larger gap to span. And you want to do it with rigidity in mind. Definitely have something on the clasp, because if you can imagine, that's going to flex and move potentially. So you want to have that supported, very well supported, and then just kind of evenly space your sprues, connectors, whatever you want to call it, around here. Now, one of the really cool things about Millbox is actually this line here. This is telling you where the high point is vertically. So the easiest way to think about that is everything above the line is going to be milled from the top. Everything below the line is going to be milled from the bottom. And so when you're doing your spruing, when possible, try to put your sprues right on the line, because that's going to keep you from having to remove material either above or below the sprue after milling. So you'll just get a cleaner result. Then we'll throw one right here on the anterior aspect. And this is, you know what? Probably use an extra one right here. There we go. So this is essentially what we're going to look for. And the test for this, if you've done it correctly, is after you've milled it, while it's still in the puck, just take your fingers and try to move the restoration in the puck against the force of the sprues. If it's mobile, then you need to sprue it more rigidly. If it's rigid, keep your method right, just how you have it, and move forward. So done with sprues. Yeah, go ahead.
If I could add, you know, I always tell people, if you think you put enough support pins or sprues, put 2 more. If you feel like you, because I'm going to tell you that the calls that I get for technical support, everything seems to go fine. Guys are designing them. Maybe they design a little thin or something happens and they just, but when it comes to just fit, it comes from those support pins or those sprue pins.
Right.
And so there's a lot of times where I might even put 2 on a clasp, put one at the tip and one at the base. I'll put, you know, like I said, the big thing is if you feel like you put enough, put a couple more, because it's not going to really add that much to your mill time. As long as your tool can fit in between them, you're good.
Yeah, in fact, that's a very good point that I was about to bring up there, Chris, about the tool fitting in between them. So if you have another sprue, like say right next to this one, the area that you create between them must be larger than your tool. And you can kind of eyeball that, but if it's not, then you can end up with binding issues, or it might not mill some material there. It can just cause you a little bit of a headache. So you do want to keep that in mind, but definitely the name of the game with this material is rigidity. So yeah, thanks for the addition there, Chris. So then we'll jump on to the calculation phase, which is actually very simple. You wait a second, at about 5%, it'll prompt you for the install, or the strategy. And this is our monolithic mono strategy for it applies to dentures, it applies to denture teeth, RPDs, splints, all that sort of thing. If it's one piece, we're using that strategy. And this guy, the default for the strategy is actually to rough with the 2mm tool. So if you want to utilize all the benefits of the 3mm tool, just make this selection here. And then a couple of words on the other ideas here. The 5-axis options, you have either 3+2 or 5-axis continuous. I recommend just sticking with a 3.2. It really gets like 99% of all cases. The continuous is just more, it adds mill time and it adds calc time. It's good for fancy or really complicated things, but generally the 3+2 is good. And then next, as far as the detail goes, with an RPD frame, you don't need to go lower than a 1mm typically. But if you do want to go and get a little bit more detail, you can select the 0.6 and it'll detail out with that. You know, if it were a Snap-on Smile or something, I would certainly use the 0.6. But then we'll hit OK and it'll start calculating. Now the calculation time on this is only a couple minutes, but in the interest of time, I've already got it calculated in another window. So as it's running calculating, it's going to tell you the tool slots. So make sure that those match. Otherwise, you can have some trouble. So you know your big tool needs to be in 5, 2 and 6, 1 and 7, etc. So jumping in here, I have the calculated file in a simulation. And let's see if I can drive this here. You can see what the end result is. I'm a big fan of this cinematic simulation. It only takes a few more minutes, but it gives you a view of what you're going to get. And so, especially if you're new to this, or if you have a design you're not sure about the way it's going to mill, definitely use the simulation. It's a very good tool. So on with that, you know, if there's any questions on this part of the workflow, you know, like Katie said, we'll be happy to answer that going forward. But that's essentially the nesting process, and then it's milled, and we're off to the races. Oh, one more thing before we switch over. The milling time here that you can see at the bottom, this is real life, so this is quite accurate with Millbox. And generally, the RPDs range from 90 to like 120 minutes, depending on the detail of the design. So essentially we've gone from a 4 to 5 hour process time to a sub 2 hour process time, which is very cool. All right, so go ahead and switch it over, Katie, and then Chris will take it, and then we'll do some Q&A here at the end. Thanks.
All right.
I see you, Chris.
Yeah, I'm trying to. Give me a sec. All right. All right. And so this is what you'll end up with after you mill. And as Greg was saying, it's almost polished. It is almost ready to go when it comes out. You will hit it with maybe a little pumice or the polishing kit that Meyerson has with these embedded bristle brushes, and you'll spend 30 seconds, a minute hitting those and giving it maybe just a little bit of a high shine in the areas where you cut off your support pins. But you can see support pin here, 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 up in here, here. I try sometimes to avoid this outer edge. Sometimes you can really sneak it close, and this can become a little flexible. And depending on your mounting bracket, depending on the machine you use, sometimes that can be unsupported. So if it is, don't put any support pins there. Or move it in a little bit so you get more thickness. Or if it is supported, if it's like a lot of the Rollins totally surround the puck, then you're fine. But that's something to consider. Here's the outside again. It's got a shine going. It cuts it so nice. VisiClear, all right? So the VisiClear is a different material from the Zerlux acetal, but a lot of what you saw as far as design is the same. The only difference is you're gonna go wider with the clasp, even more so, even more of a wing type design because it's a more flexible material. And so, we're looking at probably a millimeter to a millimeter and a half wider than you were even doing it with the Zerlux acetal. So we kind of have traditional clasp, we have acetal, Zerlux acetal clasp, and then VisiClear clasp. We also have the Duraflex. Duraflex and VisiClear are essentially the same material. It's just Duraflex has a pink pigment and VisiClear is mostly clear. All right. So we all have a reason to need to repair materials, whether it be fixing a case that's old, adding a tooth or a clasp or something, or let's say a doctor doesn't give you the greatest impression, like this case here. So this is a typical where the interproximals and everything didn't really get captured in the impression. And doctor sends it back and says, patient's collecting food as they eat along that lingual. Can we correct this? Well, if this was metal or this was anything else, you're looking at a remake. With the acetal, it's very repairable. There's a piece of equipment called the hot shot gun. Some of you guys listening may have it and some may not. It's a handheld injector. With this handheld injector, you have the ability to melt material to the base material. So Duracetyl, which is the version of acetyl that can be injected in an injector, right? So a Valplast, the Flex Press, TCS machine, any of those that inject those materials with just a change of the programming times and temps, you can inject them. Well, they also, these materials work in this handheld injector, and they will melt to the millable version. It's not different, or not very different, not so different that it can't be injected to it. So what you would do is you'd wax this in, all right, filling in those gaps and spaces that are evident. You'll then do a putty matrix. Once the putty sets, you'll then boil that off and get it real clean. Then taking the hot shot gun, which again looks like kind of like a big glue gun or caulking gun, and then a little torch that I recommend. If you guys want more information on this and kind of see it live, go on to Meyerson's YouTube channel, and there's videos on there of me doing repairs. There's videos on there of me polishing, all kinds of stuff. It'd be good to look into that after this. And so you'll heat and you'll go along and put a bead of material along there. Then you'll take the putty and you'll smush it down into place. This material, whether it be Duracetyl, Duraflex, or VisiClear, they need a push. When you put the material on there, you can't just let it sit on there and think it's going to melt to what it's sitting on. It needs to be smushed in. And so that's what the putty does. And you can see here it'll ooze out, and you will have flash that you'll have to clean up. But once you clean up that flash, you'll see it'll be perfectly adapted to that lingual now. And now this is ready to be clean, polished up. There's a appliance called a Snap-on Smile. If you want more information on that, you can contact Jenny at Meyerson. It's kind of been released, but you have to attend a webinar to be trained on it. You also have to do a test case. And so, that's an acetyl resin. That's our Zerlux acetyl, or it's specific material that's been developed for the Snap-on, but there's always a need that whether it's a bad impression, whether something happens in your mill, whether you block out too much in your software and you realize it afterwards, we always have reasons that need to repair. And so that's an instance here where this is a Snap-on. These are 4 Pontics. This is actually back before we had the ability to mill it. This was injected. And we would always, when we had thick volumes of material, like in these Pontics, you'd always get a little warp, almost like when you cast metal. For you guys that can remember way back when, it's been, 5 years probably since we cast something, but it's kind of like the old way of doing it now. But anyway, cut it, fit it down, wax that in, do a putty matrix of that area. Same thing you saw before, heat that area, inject a blob of the acetyl, smush your putty down into place. You'll have oozing of the material. You'll have all that flash, but you'll then clean it up. And then here's our joint, all right? Here's the lingual, no line of demarcation. It's a 100% melt. Now you'll notice this pink. This is acrylic, but this is locked on 100% mechanically. There has been channels up inside these Pontic areas and the acrylic's locked on there. So I don't want anyone to have an illusion that acrylic will chemically bond with acetyl. You put a drop of crazy glue on acetyl, let it set, and you can flake it right off. So I don't want any illusion there. This is held on mechanically, but you can do it, but you have to do it mechanically. But no line of demarcation. So as you go along, you may have a shy margin. In other words, as the material rolls into that cemental enamel junction between the tooth and the and the gum line. If that doesn't quite adapt nicely, that's a famous area for the doctors to miss in the impression. And then you make the snap-on thinking it's really nice and adapted, and that winds up being open. And then when the patient smiles and they relax their lip kind of catches when they eat food, it traps in there. Well, this is a real easy way. You wax it in, putty matrix, boil it off, clean it, heat, inject, smush. And you'll be able to correct a lot of those things. This case here was kind of a hybrid, 3 anterior teeth, 2 posterior. That's the only teeth in the upper arch. These, as ugly and broken down as they are, they're actually healthy. These are actually healthy teeth. So the doctor didn't want to extract, patient didn't have money for crowns or anything like that. So really we just needed to make a partial, but you know, aesthetically, you know, there's 3 things that a partial accomplishes. 1 is to allow the patient to eat. 2 is orthodontically to keep all the other teeth from drifting, keep them in place. And then 3, it's aesthetics, and that's somewhat in that order. Problem with that is if it's not aesthetic, the patient isn't going to wear it and they aren't going to eat with it and or keep teeth in place orthodontically. So really aesthetics is supposed to be the lowest on the rung of importance, but it becomes pretty important. And so what I did is I came up with this. Right? So we went over those teeth in the anterior like shells. We did pontics elsewhere. We have rests and clasps on these teeth. The patient occluded here, but did not occlude anterior. She drifted forward, protrusive with her lower jaw to actually make lingual contact. So I didn't have to do anything there. But if she did make contact, we could have opened a window here that she would have bit through, and we wouldn't have had to affect her occlusion. Meshwork here. The doctor felt like there would possible need for relines in the future, maybe even a soft reline. So we wanted acrylic there that would bond all that. So we decided to do finish lines and everything to apply acrylic and denture teeth. We have clasping here, which is for retention. We'll also get some retention from going over those anteriors. Here it is a try-in with the posterior teeth set and wax. And here it is finished. And so it's a nice tool. It really is a nice spot. You know, the low option, least costly option for the patient was just a partial. The high-end option would be implants, crowns, partial, you know, multiple combinations of something that would be much more expensive. And then this is a nice spot in between. This should, you know, labs should charge more for this than they would for just a regular partial, but it won't be anything close to a case that's implants or prepped teeth for crowns and partial and all that. And it's a really nice, you know, change for this patient. And it really fits a niche, and it's a really nice thing to be able to offer to your doctors. All right. So now, you know, Greg, I don't know if you have anything to add. We can kind of answer some questions at this point.
Yeah, there's a couple of questions I see here, and now definitely submit questions now at this time if you have any, and we'll run through those. One thing that I wanted to add is, you know, if you are running a Roland and you want to try out the solution that I showed you guys, you do need to be on an updated version of the software. And so if you can contact your support, or if you have any issues, you know, feel free to contact me directly, and I can point you in the right direction. So just wanted to add that. Now, there's one question on here about wet or dry mill, and so correct me if I'm wrong, Chris, but the material can be machined either way.
Yep.
But it's more typical to be machined dry because there's more dry mills out there. You know, it's good to machine it wet. In fact, you can push it a little harder when it's got coolant on it. But the solutions that are being put forward right now are dry mill.
Correct. I would agree with that totally. And I've been milling it for 4.5 years and have never had an instance where it, you know, pushing the speeds and everything, and have never even had it attempt to melt or cause any problem like that. One thing I have seen, and Greg, maybe you can touch on this,
Mhm.
I've seen some softwares, and it probably has a lot to do with the gap, but I've seen it where the base of the tooling will actually hit the puck on the other side of the gap, and when it hits extreme angles, and it actually doesn't hurt too much, but what it does is it builds friction up there, and it'll
Mhm.
actually heat the tool, and then the tool will actually melt into the base. So I've seen that a couple of times with people, and I'm guessing we just got to create more of a gap there so that that tooling doesn't hit at an extreme angle.
Yeah, so that's actually something I'd like everybody in the industry to know about. So the CAM software, the reason that happens is because there's a mismatch between the physical tool shape and the shape that the CAM software thinks the tool is. And so those two things have to talk to each other. They have to work well in order to avoid those impacts. And that's another unmentioned benefit of using Sierra tools through Zahn, is that all of that validation has already been done in the software. So if you're getting impacts, basically it's a software update. Make sure you're all up to date, and you're going to be good. Now, making the gap wider helps because you're just giving it more room. But the root of that issue is just a profile mismatch in the software.
Yeah, it kind of becomes a band-aid, and you wind up taking way more space up in the puck. And on a
Right.
big case, you may not be able to fit another partial in that puck, and it becomes a waste of money. So why put a band-aid on something when you can actually have it dialed in very
Agreed.
specific? And yep.
Yeah, and that also works. I mean, all milling. If you have any sort of impact, it is a settings issue. It's a tool shape issue.
Mm-hmm.
Let's see. I think we've got one here. We've got a question about Hyperdent, whether the Roland can run it. Yes, it can. There are some labs out there doing it. I would suggest reaching out to me, and I can put you in touch with. We can work with your reseller or what have you, so we can get you running if you want to go that direction. Does Razor Sharp work in zirconia in the green state? So the tool that I presented, the single flute geometry, is a plastic and wax geometry only. It is not designed to work in zirconia. Now that said, the other tools, the two flute tools, while they're specially designed for these materials, they can be utilized in zirconia. But really the best way to go in zirconia is diamond coated, because your cost per unit is so much lower, and it's just way more economical for you. Let's see. Seems like most of the questions are about tooling, Chris.
Yeah,
So
no, that's good.
I'll hit them. I'll go one by one here. So running on the D50, Roland D50. No, completely validated. Go to town. The solution's there. See, the good thing about that system is that they've used the same tooling and essentially the same strategies throughout the different machine iterations. So everything's backwards compatible. Let's see. Okay. So there's a little confusion here. There's a question, says 25-minute framework on roll and mill with a razor sharp. On the last case you designed, it said 114 minutes. Okay, that is, I was only referring to one stage of the machining taking 25 minutes. So the total machining time on the case that we presented is 114 minutes. But the first step, which is the mass material reduction, is around 25 minutes.
Yeah, so you're gonna use what, 3 tools through that process, correct?
Yes. Yeah, it's a
Yeah,
three-tool process. Exactly.
so just that
And
one first tool is what you're talking about, and then
yeah, and that's where we're saving the time, because if you use the smaller tool to do that same step, that step takes hours. And so that's really where the rubber meets the road. Let's see here. I think that's pretty much it. Are there any other questions out there, or did I miss anything, Chris?
I don't think so. Seems like we did a pretty good job at answering or getting the information to them.
Oh, that's good. Either that or people are shy. Don't be shy.
Yeah, yeah. And that being said, with Greg and or me, we're very accessible. So if you feel like there's something that was more involved or you don't really want to ask on here, don't hesitate to get in contact with us, and we can get that question answered kind of more one-on-one possibly.
Oh yeah. There's a new one here. Is it going to be available for download? So usually within about a day or so, Katie will have this posted to YouTube. And Katie, correct me if I'm wrong, but you'll send out like a follow-up email that'll have the link. Is that correct?
Yes, correct.
Okay. Yeah, excellent. So anybody who wants to see this later, it'll certainly be accessible on YouTube. Let's see here. All right. Well, I think we're in decent shape here. Chris, you want to tie it up?
Yeah, so I think the big thing that you guys can take away from this is, the design, if that's something you were interested in. I think this, between the two of us, was a nice combo. We kind of talked about it before we went on. It was a good 1-2 punch. So hopefully this gives you a good, this is a foundation. I think there's some work to be done if you're just going to get into milling these materials to practice, to get into this. It's a good start. And then as far as it making sense in the lab, kind of the title of this being profitable, we can't have something in the mill for 4 or 5 hours. And what Sierra Tooling is doing is just mind-boggling. And like I said, it's all of a sudden, 3D printing was the big push, and now all of a sudden milling, we have all the good materials. On the milling side, they're ready to go and they fit nice. On the 3D printing side, they're making advances, but those materials, even if we have some cool materials, a lot of them aren't FDA approved yet. And so we're now speeding up with these toolings and these strategies, it's all starting to make good sense, kind of on which side of it you go up. And so I think hopefully that's the info we got, across to you. And yeah, I hope it was worth your time.
All right. Thanks, Chris.
All right, great.
Appreciate it, guys. Well, hey, thanks everybody for attending again, and don't hesitate to reach out if needed.
Great,
Thanks,
guys.
everyone.
Thanks
Have
a
a
lot.
great day.